Draft science video. So, yeah, I was going to make this video earlier. So anyway, I have, it's one of those eureka kind of things. I'm trying to think of the word to use. When you got this bona fide thing, but there's some other word, I just can't think of it, like precedent, or you establish your claim by identifying a piece of the treasure. That's where I remember the word from. Like if you found treasure, it's not really worth anything until you can until you can prove that it's treasure from 500 years ago or something. Then it's worth a lot of money. But you have to be able to establish a precedent and a relationship. Well, anyway, it's not really the same thing anyway, so I probably shouldn't even look for that word. But anyway, the point is this is one of those moments, one of these things where once you've established this, there's it's totally incompatible, and it's just such a piece of, it's just so solid that you have to account for it, and you can't account for it with regular quantum mechanics. So anyways, this two-slit stuff, figured it out. Richard Feynman. So this is from his Auckland. And this is where he says light's a particle. He says it through the whole thing, but I just want to throw that in there just to establish that that's what Feynman thought. And so all these people who say light's a wave, yeah, no. But anyway, he was wrong about some other stuff. He's saying, it's chance, and there can be no explanation, and that's just kind of silly on his part. So anyway, we'll start with, I'll give you a diagram, and then I'll explain what's happening in the two-slit experiment pretty completely, and then I can just to add, the only thing that be added is the mathematics, and they kind of already exist. So yeah, but I'll explain what the mathematics is really describing. All right, so if you have a wide slit, so we made it wide, and then you have a narrow slit, we'll make a little slit. And then you have this idea of the two-slit, but just for the sake of this argument, I'm just going to draw the two-slit in a very unusual way, in the sense that, let's say a tiny slit, a tiny gap, very small everything, okay? And this will create patterns, okay? So the pattern in the single slit would be, so the size, that the up and down will be how strong the light is, and the rest of it's just the idea of the pattern. So the intensity is the length. And then in the single slit, you with a very narrow opening, that's when you get this idea. It's longer and simpler. And then with this tiny slit, tiny impediment, this is what you almost get. You almost just get circles, pretty much. Alright, so it gets very, so anyway, so those are the patterns. And so the double slit also gives you this, I guess I'll draw it just for the sake so you just understand. So with wider openings, you'll get the pattern that is basically, it gets bigger, and then it gets biggest, and then so going both ways. So it does this heartbeat kind of thing, where it has a variance in it. Okay. So I was thinking about this, and trying to figure out what slit is causing what, how the two-slit is functioning to create two patterns. Alright, so let's find a good way to draw. So part of me making this video is just that I'll go, if I draw it while I'm explaining it, then I'll know what kind of drawings to avoid, because they just complicate things. Alright, so I was thinking, so this is, say I'm going to make this into a double slit, but let's just say for starters, the idea would be there's two surfaces. And I was thinking, if you compare this to something like electricity, I could say if there was a 1,000 volts between these two surfaces, there'd be a certain pattern of the electric field. Now, if I reduced it to some other voltage, 500 volts, that pattern would change, obviously. And if I stick an impediment in, another surface in, that's essentially what I'm doing. I'm taking the 1000 volts and now making it two 500 volt surface, two 500 volt gaps. Because it won't maintain the high voltage anymore, because it's the breakdown voltage, or whatever you want to call it, and it'll break down. So, in thinking about that, gave me the answer to what's happening in this double slit pattern. Is that really what's happening is these two surfaces, this surface and this surface, are both thinking, okay, even though their total gap is big, they're thinking this is the only gap there is. So they're really doing the original single slit at a relatively narrow gap. So unless they widen this, made these slits wider, that's what gives you more of a bar pattern. It gets rid of this when you start widening this. And so this is essentially now like a 500 volt instead of a 1000 volt gap. And so what these two sides are basically doing is they're just doing the original single slit. They're doing that pattern. And so they're creating the stuff that's going like this. And then the big one in the middle. And then a little one over here. So that's what they're creating, these two, in terms of pattern. And the one in the middle is the tricky one, right? Because its gap is going this different way. So it's all really about these, changes in distance between surfaces. And so that's what Feynman's talking about here with reflections on glass. And ironically, or tellingly, he never uses the word interference. He's going to draw the pattern, and yet he's never going to use the word interference, at least in the part I played. And he's just going to do his clock thing. Now, no one ever does the clock thing on the double slit experiment, but it's the same thing. You're just really talking about distances between surfaces, which is kind of ironic, or telling. So anyway, so what I'm saying is happening here is obviously these are being, so these refractions, or whatever you want to call them. So even though this drawing is not to scale, what's happening is that the light comes in through here, close to this surface. It's doing this. Okay, so it's reflecting in. Probably. Okay, to create this pattern. And this is doing the opposite. So this side is going to go this way, and this way, and this way, and this side is going to do the opposite. And this center impediment is the one that's got the bigger aperture. So most of the time when they do the two slit experiment, this has a big aperture in the middle. So if they use the wire, then it's going to get then it's going to do this big circle-y thing. Then it's just going to do blobs at the locations. So a little wire in the middle. So they usually make this gap as wide as at least a ½ millimeter. The wavelength of the light, and so it's rather large. And so this large, so I should have drawn this larger, so I'll know that in the future to make this bigger, because this is bigger than the openings, generally speaking, when they do the experiment. So this is wider than these openings. So with a wide, if you narrow it, then it's just going to be blob, blob, blob. If you widen this center thing, that's when you're going to get all these little lines. And they're representing the field, okay, in here is different than the field here. So as you change the width of this thing, you change its field pattern. And so this is the one creating all the little bars. So in the double slit experiment, the little bars are being created by this, and the big humps are being created. So that's a good way to color. So I'll do the lines next time in black, and then you know, do the green to represent this. So when I do this video more professionally, you'll see that. So anyway, so that's what I'm telling you is happening. So as you make this smaller, you get rid of the little lines, and you end up with this pattern. Just ball, ball, ball. And as you make this middle thing bigger, you get more and more lines. And obviously there's a point where you'll go too big, and then you won't have two slits because you won't have enough light. But apparently you probably could go pretty wide, and then you'll just end up with two patterns next to each other, I guess, eventually. You know, something like this next to this, or this next to that. And it'll just be two separate patterns, completely distinct from each other. But that's the catch. So the wider you make this, the more pattern you get, the more bars you get. So, and the smaller you make it, the more likely you are to have blob, blob, blob. And so that's why when they have a gradient, which is a whole bunch of these little lines, okay, 500 of them per inch, 1,000 of them per inch, these, when you shine light through one of these polarizers, as they're called, well, no, I don't know whether they're really, well, whatever. Yeah, I don't know. I mean, polarizers are different. So the films that polarize light are different than gradients. But I guess the difference is in just how many lines there are. But anyway, you'll end up with a thing that creates blobs. And what will happen is you'll get you'll be able to see the color separation. So the reds will, go on one side and the blue on another, and they'll bleed in these bars. But only in those bars. The dark spaces will still be relatively dark. And well, it depends on how many. Like I said, the more lines you have, the more you can use it for that separation purpose. The real point I'm making is that these blobs are being created by each line is making a contribution to the blob. I mean, it's just doing this over and over again, so close to each other that each circle is just a little bit off of the other circle. Like this, one circle might be a little that way, one circle's a little this way, from end to end. But it's a minor amount of spacing, so they all end up looking like they're in the same place. But they're all subtly a little different. But it's just doing the same thing over and over and over and over. So it's just a single slit thing all next to each other, and the space is small enough. You always have to remember this is a projection, that either the lens in your eye is going to change it, or if you're doing it, if you're using this to project, you're projecting at a distance to see any of this. And if you're using your eye, the lens in your eye is compensating for that distance problem. But the point is this represents a large distance, in theory. That's either compensated by a lens or it's a distance. So tiny variations here would mean nothing here, in a sense. You wouldn't be able to tell the size of the spacing here is, just millimeters. And so obviously that doesn't incorporate into anything major here. It's just the same pattern. Well, I'm just trying to get to the point that it's the same exact single slit, double slit experiment done over and over and over and over, and it's all projecting on essentially the same location. That's the point. Alright. And the point that they're a little bit off just makes it spread more, so you can see more of the color separation if you used white light. Alright, so now the explanation. Alright, so here's the surface, let's say, make it big, and I guess for this diagram you might have to look at it at a different angle. But the point is that the argument I'm making is that this is a phenomenon of the free electrons. So free electrons are what's causing this surface phenomenon. And the surface phenomenon holds for glass reflections. It holds for, well, it holds for everything. The reflection of color. This will explain all refraction and all reflection are affected by this surface phenomenon. The surfaces is what are causing the effect. And the surfaces are like a prism. I could draw the prism and you could sort of get what I'm saying. What's happening with a prism is this surface, okay, the electrons are lining up with the flat surface. That's what they do. Okay, they space proportionally and they want to go to the protons. So they're not bound electrons. They're not part of the glass in any real way. They're just still feeling the gravity, so to speak, the magnetic pull of the protons. So they're like being another, let's say there was another Earth, but it was closer, not as close as the moon, but closer than like Mars. It would be in an orbit that would be kind of you know, where it's bound, but if it was close to the Earth, the problem would be and say the Earth were electrons and they repelled each other, it would have a problem because it couldn't get past the Earth. If it was orbiting, it would be irritable to the Earth. So although it was orbiting the Sun, it would be irritable to the Earth, and that would cause a friction problem between the two. I mean, the opposite is true. And the reason why plants have separation is just because they would crash into each other and, you know, smash each other to pieces. So they have to, the only ones that survive are the ones that are far enough apart that they don't have any likelihood of affecting each other in any strong gravitational way and start ripping each other to pieces. So anyway, so there's a bunch of electrons bound, and they're bound in strict geometry. So you can sort of understand that especially if you have a smooth surface, the smoother it is, the better, that the electrons would be all proportionally spaced side to side and proportionally spaced, you know, height-wise, and that there would be a pattern that's essentially the on-off pattern. There it is again, right? They wouldn't line up straight because they can compress more tightly if they line up triangularly to each other, kitty corner. So there you see it right there. There's the on-off, on-off, on-off pattern right there, and, you know, quite obvious. So anyways, these free electrons are always heading for the surface. Okay, they're always they're bound. They want to go to the surface, but they can't because they're locked in a magnetic field. Okay, they want to get to the protons, but there's electrons in the way, bound electrons, and those bound electrons are saying you can't get in here. So they want to get in. The overall field potential is in, but there's this guy and the soldiers are in the way, so they have to stay far enough away from the soldiers, and they're just kind of in this neutral position where they're locked between two forces. And the point is, okay, the trick of this whole thing, the thing that creates this stupid sine theta parabola thingy, okay, is the fact that that's where they want to go, though. They want to go this way. And so the point is, as soon as they get any energy, so let's say this is one of these electrons sitting there minding its own business, and it gets hit with a photon. So a photon comes in. I guess I should use different colors for that. So the electron doesn't move straight. It moves in a parabola, okay, that's accepting the fact that it's going to gain the acceleration of the photon, so it wants to do some of this, okay, but what it's actually going to end up doing is this. Okay, so that's what it's going to end up doing. And depending on how it gets hit, what color lights, and the reason why the light change, well anyway, let me just finish this argument first. So it moves off of that straight line because it tends to want to go this way, but it can't go that way, so it ends up getting stopped because there's this pressure from the electrons. So it gets this little burst that does send it off course, But the real trick is that it's going to rebound to this, back to this location, because this is its safe location. See, there's another electron over here. And so we know as soon as it heads that way, that's not going to work, because this pressure is going to say, F you can't come this way. The two electrons don't like each other. So this is part of the reason it's getting bent, is because it can't move in the direction of that electron, because they're all bound to each other. And that force is stronger than this force. So this force forces it in. And then, like I said, the secondary pull is the fact that it still wants to get to this proton. But again, it's hitting this electron. So there's two electrons. There's this electron pushing this way. There's this electron pushing that way. But there's the overall pull towards, I want to go that way because the protons are here. Okay, so you just add that. You just add up basically the idea that there's these two competing forces. And so anything that's trying to go into that force, like I said, it's being locked by a certain kind of pressure. But anyway, so it goes in and it bends to that field, and then it rebounds back. And when it rebounds is when it emits the magical new photon, okay, at the new angle. So instead of the photon going this way, the photon goes the angle it was bent at. Now, frequency dependency here gets kind of almost obvious. That, say, you're doing this bent parabola thing. Let me find a new location to draw this. It's kind of simple because you can just think of it as a timed question. Okay, so it's going to be a parabola, and it's going to move like a certain amount of distance. So the say a photon comes in, and I'll just draw it and then I can explain it. So this is, you got this kind of an effect, and then you have this kind of an effect. All right, and that would be the difference between blue light and red light, in the sense that two photons hit, okay, 2 tons, so that the frequency of the light would indicate 2 impacts before there was a rebound. So another way, I just want to emphasize, so I'll draw it one more time just for clarity, is that what I'm saying is happening is that the electron's moving in a pattern, and I'll make it a little eccentric, and it gets to a location where it can't go, and it can't do this. It can't do what it's trying to do. The forces stop it and change its velocity. Stop its acceleration. And it accelerates back to where it was. And that's when it releases the photon. So the photon's energy was in here. The energy is being repressed. The velocity, the acceleration is being rejected because the electron has nowhere to go. And now the electron has to get rid of the energy, so it releases the photon. And now it goes directly back to its location. So it does this in a straight line vector, where it did this in an arc, that kind of thing. But anyway, this is the equal but opposite reaction, is actually the photon leaving. So reflection, so what I'm saying is photons absorb, electrons absorb, alright, distractions and such. Physicists shouldn't have to put up with that. Anyway, didn't get anything done. Alright, summation. Where was I? And then I'll get to the Feynman thing and such. But there's just so much to this. Okay, so this idea of free electrons is really the whole game. And they're behaving much like unfree electrons in that, science says, they use this energy level thing where the electron gains a different orbit and all this kind of crap. And that's not really what it's doing. It's the tension between the electrons. And what the electron is just doing is this reflecting thing. It's reflecting in the same direction as the photon left, but I'm just saying it's basically a reflection in the sense the electron attempts to move. It can't move to a new location, so it goes back to where it was. And when it goes back is when it releases the photon at the new angle. And that's all. So when they talk about electrons changing their energy level, it just means that if you think of it, use a new piece of paper, as the magnet analogy. Taking the caps off ahead of time. And so these are the positions of, say, electrons, and this would be the proton. These are fixed locations. And so what happens is a photon hits the electron moves. Okay, it can't maintain the movement, bounces back, and it's the bounce back that releases the photon. So it just depends on how, it releases it and then releases it to another electron. This electron gets hit, and the photon is returned to its old trajectory based on the movement of this electron. This should be the opposite movement or something. It's that kind of thing. So in materials that are transparent, it just means that the molecules have a tendency to replicate inversely the angle of reflection, and it just ends up reflecting, say 3 reflections could end you back up with the same reflection, that kind of thing. So this one goes here, and then this reflection ends up being the one that's the inverse of this reflection, that kind of thing. But that's all that's really happening, and it's these field electrons that create charge, that all surfaces collect charge. This charge electrons behave the same way. They have the same kind of tendency to do the same thing, which is they get accelerated. They can't maintain the acceleration because of the field energy around them, so they go back home. And it's the reflection going back home that requires them to release the photon, the energy. The energy that put them in the new location. Okay. Alright, so we got this down pretty much. Okay, so the tighter the lines, the more circular or definite the pattern gets. It gets converted into just a bunch of little balls. The prism is basically working because the electrons tend to want to go towards the surface in a straight line, perpendicular to the surface. That's their force tendency. So when the photon comes in at an angle, it's bent, and it's going to be bent by this frequency. The frequency of the impacts will dictate how the bend is. So the bend can either be it'll be more or less depending on how quickly the second photon shows up, changes how much the bend is, and changes this angle. So this angle is changed based on the frequency, and that explains why blue light has a different pattern than red light. Red light has a wider pattern, blue light has a tighter pattern. It's because red light allows for there to be more bend, where blue light doesn't allow it to bend as much towards the surface. So it bends less towards the surface as blue light, bends more towards the surface if it's red light. This perfectly explains a prism. Alright, 2 slit, we already did that. Alright, so I think we got this all covered. So yes, in the 2 slit pattern, the bars are being made by the center impediment. So widen it. The wider you make it, the more bars you'll get. The thinner you make it, the less bars you'll get. And the exterior, the outside surfaces are creating basically the single slit pattern. So these surfaces are creating light in this entire area, and this entire area, and this entire area. And this one is creating bars in that area. Yeah. Not exactly. What do I want to change? I want to change, yeah, these are bars. Sorry. The single slit does create bars. It's just that the bars are inside this pattern, and in the single slit, I'm just trying to think. No, it's, yeah, okay. I have to look at some single slit patterns to see, but there may be a translation of, obviously, these different compressions of field energy. Okay, the center one's going to be doing something different than the end ones, but they're going to translate into each other. So I just don't know how many bars the outside one's going to create. I mean, it's obviously the single slit at a wide aperture, which would be have bars, but bars with breaks in them. Yeah. Well, anyway, that one might have to, I might do more, this is going to, I'm going to have to do more work on some of this stuff, but, that one's, I probably don't have a problem, but, I have to be more articulate. But anyways, it's just about the arrangement. So again, like I said, you can almost find the pattern by looking for it in other places, and I'll point that out with Feynman, that this on-off pattern is a geometric thing. It's not a wave thing. It's a geometry thing. So let's play the Feynman thing and connect two slits to two layers of glass. It's just kind of funny that they never did that, because it's quite obvious almost that exactly the same type of thing is happening, and it's all dependent on where the photon goes through. So there's no probability involved beyond the probability of where the photon goes through. If it goes close to this surface, it's going to do a specific thing. If it goes close to this surface, it's going to do a specific thing. That's what's making the pattern. There is no interference required, and that probability is not, as Feynman's going to imply, the probability is something nature's producing, that it is varying the circumstance, and it's not. Oh, shit. Guess it's going to be one of those days. Yeah, okay, back again. I really hate editing videos nowadays. I don't hate it, it just uses up time and such. Anyway, alright, so let's play this Feynman stuff and comment and such. So he's talking about how to explain quantum mechanics, and so he's getting to his whole clock thing, and he's already said things like, you're not gonna believe it, but just believe it, and that kind of stuff.
Waves don't operate this thing.
So he said waves don't operate this thing. So he's pointing to this electron, and the photon thing. These are not waves, they're things.
When you turn the light on, this might go off at any moment. You don't have to wait for a certain length of time. Of course, there's odds that it goes off at any instant, but it could accidentally go off the moment you open the slit. So it's not a question of waiting for the energy of the waves to pile up or anything. It's hopeless. I have to start with light as particles. Waves explain many things, but not light. It's particles, okay?
Okay, so there it's out of Feynman's own mouth. It's particles. Alright, so yes, he'll accept duality in the sense that, oh yeah, well, its function is wave-like, but the thing itself is a corpuscle, a particle, a thing. So I'm just saying, it did come out of Feynman's mouth, so he's the king of quantum mechanics and blah 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 blah. So all you people making arguments, it's particles. You want okay, the math is waves, the reality is particles.
It's photons. The problem is they're reflected with probability. Now the next feature, having to do with reflection again, that I would like to describe is something that you're also familiar with, perhaps not so directly, but perhaps you've seen the colors in soap bubbles. It's made out of soap water, which has no color. No color, I've seen the colors. Mix it together, get a lot of soap water together and look at it.
Sorry, that part's a little boring.
You take oil, which is a sort of a yellow fluid, and it drips with blackish yellow junk. It drips out of an oil.
Yeah, but it's a blackish yellow junk. Yes, it's yellow before you use it, and it's black after you use it.
Would be on a rainy day. You must have experience here with that. And you look at the puddle, to your delight, there are colors. Colors. These colors are produced by reflections from two surfaces near each other, very close together.
So that's where, there should have been a connection. That it's, yeah, this is a surface phenomenon, and there's something happening on surfaces that changes what can happen.
If the surfaces are far apart, we'll discuss it later, the same phenomenon really occurs, but it's much harder to see under normal circumstances.
Right, the same rules apply to the double slit experiment. There's still some of this diffraction happening at the edges, but it's such a tiny percentage of the overall light as you make the slits wider and wider and wider that obviously that disappears. It gets overwhelmed by the total number of photons.
What happens there is that in a soap bubble, for example, there's a layer of water.
likely partially happens because of the scatter in the atmosphere, which is also something to consider. You know, when it's a tiny percentage, like in space, the edges of the shadows might be more distinct.
And so we had two surfaces at some distance from one another. So
this is basically what I'm saying is that this should have been a giveaway. This is essentially the double slit experiment. It's just you're just doing it different. You're doing it a different way, but the same phenomenon is at play. There's a bunch of electrons on these surfaces, and it's the electrons that are going to dictate where the angles are going to be. And so that's the phenomenon. There's the surface electrons will decide direction.
Then the photon can either come down here,
and the straighter you are, so the straighter you are going in, then you're going to go exactly with the direction that the electrons want to go. So the rebound's going to be less distorted. And the more you bend this line, the more you're parabolaing the travel of the electron, and therefore the more likely it is that you're going to get a reflection back in an angle.
and reflect right away, or it can come down this way and reflect from back there. Okay?
Yeah, well, the reflection is actually light going the opposite. So this is further along into the theory, but I would argue that protons are what reflect light in terms of a true reflection. So what happens is the light goes in, it hits a proton, and as it's coming out, it's doing the same thing. It's got to go through the electrons on the outside, and so it's going through the electrons on the outside, and they're the ones reflecting the light. So the photon goes in pure, hits a proton, and gets reflected back out through that field of electrons. So it's the same thing as going in as going out. It's going to have the same phenomenon. So you have to always kind of multiply the effect in terms of the both going in and going out. You're going to have the effect when you're going face to face to surfaces anyway. When you're when you're going through slits, it's a little different because the field is only in one location. You don't go through it twice.
Now, as it turns out, it's about the same percent. If it's just water between air and air, it's about the same, 1 in 25 both times. What's the color? If I'm going to do it with monochromatic, like a light of one color,
Alright, so as I've just pointed out, we know what the colors are. The colors are the different frequency means that the electron moves further in the direction of the surface. The wider the wavelength, the longer it takes to get hit that second time, the further along in terms of a bend. So these bends are tiny, but I'm just, I have to exaggerate them to kind of make it more visual. But that's what's really happening.
You see in color. What you see on an oil film, on a mud puddle, or in a soap bubble, when you use light of exactly one color, is not colors, but bands, bright and dark bands. Places where the light is reflected very well, and places where it's not reflected at all.
Right, now, so he doesn't say like the modern physicists say, anytime you see that pattern, you know it's an interference pattern. He's not saying that, right? Yeah, because, no, that's not what it's just probabilistic, but it's not interference.
Across the bubble. Now, the position of those bands, if you first looked at a bubble with red light, you see bands, black and red bands all over. If you look at it with blue light, you also see blue and black bands. But the pattern is not the same. They're displaced from where the red ones were. And so when you have both red and blue, you get purple and red and black and purple and so on. Now if you add to that yellow with its pattern and so forth, you get all these...
Right. So that's just saying that depends on what photons you're reflecting at what angles from what position and blah blah blah, and they add up to different colors and blah blah blah.
Colors, mixing, okay? So we're going to simplify experimentally, as Newton did, and look at these this reflection. What Newton, most of his experiments he did this clever way. He had a beautiful curved piece of glass, which was a lens, and a flat piece. and put them next to each other, and then this was only a very slight curvature, and so he had this gap between the two. And when he shone light this way and looked at reflected light, which, depending on where you looked, see, this is a cross-section of the lens, which is more completely like that. There is some reflection in here, which is irrelevant at the moment. There's another glass plate down here. When he looked in different places, his light came down all over, and he looked in different places. He was looking at cases that corresponded to reflection with one gap or another gap between the sides. And when he looked at this with monochromatic light...
Right, okay, so this is the same thing as basically saying how thick is the glass. So this would be this thickness, and the thicker you make it, you change the reflective index of the glass. So it reflects 16% at one level, and then at another level it's almost 0, and then it goes back up to 16, 0, 16, 0, 16, 0. I'm pretty sure it's 16. Yeah, well, he makes the same mistake in the video, saying it was 8 when it was 16. But anyway, that's the real. That's what this distance thing is really saying. But obviously, from what I'm pointing out, is that these, starting off with this curve, okay, which you could say was almost a straight line. But anyway, you obviously have the orientation of the electrons here is going out, and these are going up. And the point is as the light goes through, it's going to be bent by each one of those field electrons, and that's what's creating the angle of refraction.
Looked down on it, since it was a circular, a spherical lens, he saw in what I call bands in the soap bubble, but more organized, he saw rings called Newton's rings, with a black area starting and then red, if it was red light he was using, and black, red, and so forth. These looked like they were coming closer and closer together.
Right, so there's Newton, so this is the real tie-in, right? Because you have Newton's rings here, so you obviously can't see it, but he just drew the rings, caused by this effect, and then this is exactly the same as a small aperture. So there's a connection between the single slit experiment. The small aperture also creates Newton's rings, and thickness of glass. So the two experiments really are fundamentally tied to each other based on the fact that they will create this on-off pattern. And again, when they talk about the slits being this way, it's interference. When the slits are this way, somehow it's not interference. It's probabilistic. And that's where I would argue that you can see the lack of continuity in this theory. They're getting the right answer for the wrong reasons.
But he was a clever man and understood immediately what it meant. If he measured the distance from here to here and plotted the answer for whether it's red or dark against this distance, not against this, instead of measuring away from the center, he measured how far apart these plates were. Then he found, like our friends the Mayans, every time you had 365 pulses, they had black. In other words, if this was black and this was red, then double that distance was black again, and yes, and triple the distance was red, and 4 times the distance was black, and 5 times the distance was red, and so on, nice and even. In other words, instead of measuring by this distance, by measuring the thickness, you find the following experimental results. Reflection coefficient against thickness between the two layers. Okay?
All right, so when you change the thickness, you're changing the molecular surface. And when you change the molecular surface, like say, you could imagine that if I'm compressing some molecules, that the electrons and the protons, which position exactly they are in, whether you're on the flat of a, let's say if we just made it into a hexagon where the electrons were, well, I just drew some other agon. You can understand that if I rotated that, so in this position there's 2 electrons facing this way. If I rotate it, there'll be a peak, and there'll only be 1 electron facing this way. And that's really what we're talking about, is what position the molecules will be in on the surface. And so as you change the thickness of the glass, what you're really doing is creating surfaces that have more electrons on them, and then surfaces that have more protons in terms of what's exposed. How much of the proton is exposed is dependent on how thick this layer is. And as you do that, you change the intensity of the electron's pull, and therefore you change the amount of angle that they'll bend the light. And what kind of odds to a pure reflection you'll get. But I think the pure reflection, again, I think is actually hitting protons rather than hitting electrons. Protons reflect light always, and electrons absorb light and reflect and reproduce the photon in the direction of their travel.
In this case, if it's an oil film bubble, that's the distance. In this case, it's the space in between the lens and the plate. And if you're going to change it, it's harder to change in a soap bubble under control, but it changes automatically as it dries out. You get the following. You get no reflection if the thickness is 0, then you get a strong reflection for a certain thickness, and then if you make it thick, you get no reflection, reflection, then you get no reflection, you get no reflection, and so on and on. And now it's getting thicker and thicker. Does this go on forever?
So there you have it, right? I mean, that's the classic interference pattern. And, he's not going to talk about interference. He's not going to talk about a photon radiating. He even mocks that as a description of how, when he gets to the actual layers of glass, even mocks the idea that does the photon send radar down to find out how far away the bottom is? As a ludicrous explanation, and yet that's Copenhagen. Right? So clearly it's the same function, and they just come up with two different ways to describe why, and they do it based on convenience. This creates the convenience of comparing it to water waves, which it has nothing to do with. It's just a circumstantial truth that the two things happen to create an on-off pattern, which is, again, the simplest pattern in the universe. So it's not terribly surprising that you might have two phenomenons creating a pattern for fundamentally different reasons. And as I've stated before, we know why there's a pattern in water waves. It's because of the friction with the surfaces and the tension of the water. None of those circumstances exist for photons, so there has to be a different explanation for why there's this on-off pattern.
Yep. If you got good enough monochromatic light and get the experiment under control, you can make it go almost indefinitely.
So I've played this part before, but he's just saying, you could even go a meter thick of glass and just shear off a tiny bit of one surface and change the reflectivity from say 10% to 1%.
You can make this work for distances of a meter or more. Still keeping track whether it's even, odd, bump, bump, bump. Okay?
So they do this, again, for especially, lenses and cameras, different things. They want to make sure they can, any piece of glass, like submarines was the example, where you want to reduce reflection as much as possible, so you precisely polish the glass to the perfect thickness to create as little possible reflection as possible.
So that's interesting, very interesting, but that's damning. Why? Because what theory were you figuring for the reflection from that made the reflection be 4%? The odds, 4%, whatever. You put another layer down here at the right thickness, expecting to get 8%, and you get nothing. How does the layer down here turn off the reflection from the layer up here? Or, if you figure that out, and you make the layer just a little thicker, it doesn't turn it off, but in fact the reflection is more than twice. On this scale here, this line would have been what you would have expected if you expected it always to be 4% plus.
Right. So, again, it's almost mocking the idea of it having radar or knowing what the thickness of the glass is. And that's the Copenhagen interpretation, effectively, of the two-slit experiment. And the real point is that it all happens on the surface. It doesn't happen someplace else. I mean, it happens through these angular interactions, and they're all geometric. It's all geometry. There's nothing waving. There's nothing. Well, I mean, the parabola is not perfectly geometric, I suppose. That's where the geometry is converted into a analog. So you take this very digital system of everything in a position, moving based on very specific rules of straight line force, and it becomes, like I said, if you integrate them over a period of time, that movement will appear to be rounded when technically it's not really round.
4% or 8% from the two surfaces. This is what you would have got if you disregarded all this nonsense that actually happened. But common sense, it reflects with a certain odds, and it reflects from the other surface with a certain odds, and so altogether you get twice as many coming back. This is the twice as many. But for some, if the thickness is 0, you don't get anything. If the thickness, hey, that's not such a bad idea, is it? If you don't have any water there at all, you wouldn't get any reflection. Starts out right anyway. So that theory was kind of dumb now that I come to think of it. And that helps to explain Newton's observation: when the distance is too small, the light doesn't know anything about it. If the thickness is sufficiently small, it doesn't reflect. It does exactly the same as if there's nothing there. But the horror of it is...
So a thin enough layer of glass doesn't produce any reflection. No, it has to be the other way around. Yeah. It doesn't go to 0, it stays at 16 or something. It's more reflective.
It's all right that it increases as the thickness goes up, but it overshoots, you see. And then it comes back to 0 again when the thickness is just right. It's very difficult to invent a probability thing. If I have these spots on this surface, it's very hard to see how you're going to have spots on this surface, which turns the spots on that surface off when they're the right distance away.
Right, because, well, you shouldn't use spots, but you should have figured that there are molecular differences and patterns inside of the geometry of the material itself, and that those patterns could account for differences in not only what you can hold as charge. That might be an interesting thing to figure out too, whether you can hold more charge on glass based on how thick it is.
And so Newton went a little bit nutty. And he talked about fits of reflection and transmission and so forth. And I would like to now just finish this by telling you what is the answer. Now here's the answer. This is the way we figure this out. It goes as follows. What we're going to calculate is a probability. The probability of a particular question. And then the probability that this counter goes off. The probability that if I had one photon coming down, it'll come back to this counter. The probability, which is measured by this curve. And here's the way the rule is for finding the probability. Now listen, hold your seats now, hold on. Don't be afraid, just go along, all right? Never mind that don't like it, huh? Just hold on. It works like this. What you do is you take a piece of paper.
Yeah, I don't know if we really need this part. Well, we'll play some more of it. There's just going to do the clock thing. But I want to get to the part where he's actually leaning on the podium saying, I don't like it either. And actually says that. But I don't think it's necessary to play any further, just because the whole clock thing is just a way of measuring the distance. Okay, that's all the clock is really doing, is just measuring how many times you're going through that thickness change. You're going through the wave, and there's a point where when you stop, you'll be either at 12 o'clock or 6 o'clock or 4 o'clock or one of those angles. Yeah, so I think that's it's probably enough for this video. And like I said, I'll have to do this more video of this, with pre-done drawings and all of that stuff. But I just wanted to. I think this is the Eureka. This is the explanation. It's field electrons, surface electrons, that are primarily initiating the function. Obviously the glass or the material has to be transparent for the photon to continue its course through it without being converted into just heat. And the reason why it would be converted into heat is based on the tension between the atoms. So it depends on how much they can move. And so glass is a good explanation because it's a good insulator. And so the truth is they can't move, and so there's not any extra motion, which means that there's no likelihood you're going to convert a photon into some other kind of ton. And what's really happening in other materials, like opaque materials, is that the photons are being converted from ultraviolet or green or red to infrared photons. So there's a bunch of because there's already some motion in the electron. It's because of that extra motion. That extra motion is essentially converted into a reduction in the frequency of the new photon created. So a regular visible photon goes in, and what ends up happening is it gets converted through the interaction with the electrons into an invisible photon. It's still there, still a photon. It's just that it's a higher frequency now because its frequency was broken by the interaction because the electron was already moving. If you hit a moving electron, you're going to change the frequency of the light. In other words, the light emitted. Okay. Now I have to work on that one. Right, because you have to do the double ton. The ton thing is a frequency, so I have to account for the 2 tons being released. But that, like I said, I think is accountable in the sense that it's the same way they went in. I mean, it's just a conservation issue. How to say that? I mean, reversing a process, essentially. So when you reverse a process, it's going to process at the same speed it happened at. So again, it just has to do with whether the electron is moving or not moving at the time of the event of the photon going in and then the photon leaving. Conservation will kind of dictate that the timing cycle will be the same unless there's some other source to change it, some other source of movement. Alright, that's probably enough to say. Anyway, I'm sure it's related to the movement of the electron. I have to detail that. So anyway, hopefully you've gotten the gist of this. So the gist first is Feynman in this lecture doesn't really talk anything about some huge dependency on any kind of wave function. He's thinking of it as a probability, okay, and wave function isn't part of the conversation until you get to the 2-slit experiment. And again, they're really just talking about the same phenomenon. It's light interacting with field electrons on surfaces. And depending on whether the light's going perpendicular to the surface or directly into the surface will change the function slightly, but it's the same function. The surface electrons change the angular direction of the photon by absorbing it, accelerating, and then readmitting it. That's all that's happening. The photon goes in, the electron moves at a wrong angle. That wrong angle ends up being the point at which it emits the new photon. And that's what's taking place for all of these phenomenons. Okay, enough said. Till next time and such.